hear me? Amazing, excellent. It's good to see you. Thank you so much for having me. Kalusha's been wonderful. This has been a fantastic first day to a conference. So well run. Please give it up for the AV team. They're amazing. Today I'm going to talk to you about large language models. As Tejas mentioned to you, I lead the machine learning operations team at Mozilla, and then I teach students as well, graduate students, all of whom are attempting to use these technologies in the completion of their homework, which is a completely separate topic. I won't get into that today. Instead, I'm going to begin for you with an overview of how large language models function. Then I'll show you how a model itself fits into the larger products that you probably think of as Gen AI. And then once we've done that, I'll share with you some conclusions from the body of research that we now have about the intersection between large language model usage and professional productivity. And we'll summarize takeaways at the end. Sound good? Yeah. Sweet. So, I'm going to start you off with this ChatGPT interaction. This is a bug I've come to refer to as Strawberry Gate. Made its rounds on social media in the back half of 2024. If you asked, and this wasn't just ChatGPT, this was a lot of them. If you asked, how many R's are there in the word strawberry, many tools would respond with the answer 2. As a matter of fact, I give a workshop for O'Reilly where I had people try this with all different Gen AI tools and got every answer between 0 and 3 inclusive on this question. But it seems like a simple question, right? Count the R's in strawberry. Hopefully, the tool to which all of my elite university graduate students are entrusting the entirety of their computer science homework would be able to answer this. So why do we see this happen? The answer in a single word is context. But I'm going to explain what I mean by that because I think popular discussion has a tendency to use this word in a few different ways, and I want to make sure that we're clear. Large language models are trained on prose that their build teams were able to scrape from the internet. It's from this body of knowledge that they draw their response capabilities. Now, on the internet, people don't ask about the spelling of the word strawberry in a vacuum. Usually, when a spelling query like this comes up, people aren't referring at all to the first R in strawberry. When they ask how many R's are there in the word strawberry, this is usually a person learning to write and spell in the English language, which is, of course, the shower drain of languages, and nowhere even close to phonetic. It's not like Arabic, it's not like Serbian, it's not even like Spanish. In all of these languages, you can hear a word and mostly understand how it's spelled. English, of course not. Of course, it's not like that. And so, hearing the word berry doesn't necessarily tell you whether there's a doubled consonant in the middle. Is it B-E-R-Y or is it B-E-R-R-Y? It is about this detail of the English language that people are usually asking when they ask the question on the internet, how many R's are there in strawberry? And the respondents, the people who answer them on the internet, understand this context. With the context, the question becomes, does strawberry have a doubled consonant? Double, 2. The answer is yes. And so that's where we end up with patterns like this. So, to understand the role of context in training a large language model, I want to introduce you to a much simpler model first. And I want to mention that large language models that you're used to work in a somewhat more complex fashion than this. This is not a direct correlate to the way that they work. However, I think it's going to help give you some intuition for how they work. Does anyone know from this illustration which type of machine learning model I'm about to talk about? The Markov chain, that's right. So, you see represented here on screen a model for predicting the weather. The model has 2 pieces that you need to understand. One of them is states. So in this case, the weather conditions, sunny, rainy, or cloudy. The other piece besides states is transitions, changes between the states. Each of those changes has a probability. So, if it is currently raining, and we have no other information about the weather, what is the probability that it will next be cloudy? Anyone know? 0.4, that's right, 40% chance. So, if we have no other information except that it is currently raining, we might know that there is a 0.4 probability that it will next be cloudy. There's also a 0.4 probability that it will remain raining, and a 0.2 probability that it will become sunny. The transition probabilities in a Markov model make it a quick calculation for you to determine the probability of any given chain of events happening in a certain order. Assuming you have a complete set of transition probabilities, you could also predict a certain chain of events happening in any order. Okay? These are used in real life. For example, Mozilla uses a Markov model for predicting things about long-term customer value. Now, imagine you had one of these network diagrams, but the network diagram contained every single word and piece of punctuation that had ever appeared in the Common Crawl, which collects an estimated 250 terabytes of data from billions of web pages every single month, and which has been done every month since 2008. Each transition probability points to a word that at some point appeared after the word that we're currently on. Now imagine that these transition probability arrows, we'll call them edges, don't just connect each token to the very next token that has ever appeared in that written text. Additional edges influence the probability of which word will appear next based on which word appeared 1 word ago, 2 words ago, 3 words ago, etc. We're starting to look at a really large set of nodes and transition probabilities. So I'm going to show you how language generation would work in such a model. Here I have listed out in the left-hand column several n-grams to help you visualize this. We're trying to predict the token n in the magenta row. At the n-5 position, we've got a token indicating the start of the phrase. Then, the first word in the phrase at the n-4 position is I. Next, we have went, then to, and then the. Now, on the magenta row, you see some options for what the next word might be. We've got store, movies, car, apple, parrot, etc. In the network I've described, you would have a lot of options, but I'm just showing you a few for the sake of clarity. Now, below each word, you see a prediction weight. Larger weights for words that appear more often in that position relative to the given inputs, and smaller ones for words that appear less often in that position relative to the given inputs. Let's say that for now we're generating text by randomly selecting from among the tokens with the highest prediction weight, and in this case, that's store and movies. So we select store. Here we are with store selected. Now let's move on to predicting the next word in the sequence. What I'm going to do is I'm going to show you the sequence that we've generated so far, including the store that we just added. Everything's been bumped up 1. We now have new options to select from on the magenta row. I went to the store to, I went to the store and, I went to the store apple. Note the very small prediction weight on apple relative to those of tokens that would make a lot more sense in this phrase. If you take a look at this for a second, it may start to become clear what sorts of tokens we might expect a pattern like this to do especially well at predicting. It will do especially well at predicting tokens that exhibit a very strong pattern of where they appear in a phrase. Which sorts of tokens have the strongest pattern of where they appear in phrases in the English language? The answer might surprise you. It's preposition words, at, or by, or in, or of. And it's also punctuation, like commas, periods, colons, or semicolons. These types of tokens are highly contextually linked. Their appearances follow a strong pattern. Part of the reason for the extreme utility of large language models is that they're very good at writing in these patterns of grammatically correct English. That can be really useful for folks who don't have trouble understanding English because they understand words that have a meaning that is translatable, but it can sometimes be hard to place these things whose locations depend more on their position in the phrase than on a given meaning. That's not most tokens, though. Most tokens don't get their position in a phrase mostly or wholly from just the pattern of the phrase. Instead, they get their meaning from the meaning, or rather, they get their position in the phrase from the meaning of the token itself. The token store, a place where we go to select items off of a shelf and then purchase them, means a different thing than the token movies, a place where we go to watch feature films on the silver screen. The massive network derived from text, as I've described, picks up on these patterns as well. So when words have different meanings, they are denotationally distinct. They have different denotations, different definitions, and they usually appear in different contexts. If we say, I needed to buy some apples, so I visited the blank, it's clear to you and to most of the people typing text on which large language models are trained that the next token has to be either store or something very denotationally similar to store. Denotationally similar words can usually appear interchangeably in the same pattern without affecting the meaning of the sentence. So for example, I could say, I watched the new film on Friday at the movies, or we could say, I watched the new film on Friday at the cinema. Whether a generated sentence used the token movies or cinema in this case would not change the meaning of the phrase. It might just change the perceived location of the person who said it, that's all. Now, where generative language models run into trouble is in situations where choosing a word based on the context isn't enough to get it right. That is, in situations where tokens are contextually identical, but denotationally distinct. That is, the words appear in the exact same situations, but they mean different things. Which words do that? A lot of times it's numbers. I have 3 apples, I have 5 apples, I have 4,000 apples. They mean different things, but the interchangeable tokens all appear in identical contexts. And even worse, in legal text, because Article 1-2-A is a completely different article than Article 2-3-B. However, we refer to them in our text the exact same way. Proper nouns are another one that this sort of pattern matching can struggle with. It matters whether Bob or Anna did the crime with the candlestick in the kitchen. Accusing either of them makes grammatical sense, but the phrase doesn't mean the same thing. Now, this begets a good question. A lot of times when it comes to proper nouns, numbers, dates, generative models can get it right, and the reason for this is that the context often fills in to suggest the right thing. So here we have an example phrase, Justin Bieber was born in, with several options. Now, he certainly wasn't born in apple or parrot, but the years we see as options here have higher prediction weights. The correct year here, 1994, has by far the highest prediction weight, and that happens because the inclusion of Justin as an n-x token, followed immediately by Bieber, and then followed somewhere after that by born, overwhelmingly results in the number 1994 appearing in online discourse. Models are able to pick up on this pattern because of this multi-headed attention architecture. If you're interested in it, you can read the paper Transformers Are All You Need, which came out in 2017 from Google. I won't get into it now because I don't have a lot of time. But suppose that instead of this example, we were looking at this, where we're trying to complete the phrase, the law firm Johnson and blank. A quick Google search immediately dredges up half a dozen law firms whose names start with Johnson and, but they end with a different surname. Which one should the generative model reference in its text? Context alone may not be able to provide an answer, so the selected token could be wrong. This is why you have to verify facts that you get from a large language model. A phrase that sounds plausible is not the same as a phrase that is objectively true or correct. And at this point, numerous doctors, lawyers, and software engineers have gotten tripped up in courts of law because they placed the weight of their professional credentials behind a claim or action that a chat UI suggested to them. How do you fix this? The field has begun to answer this question in various ways, from retrieval augmented generation to supervised fine-tuning, but often the quickest and most pragmatic solutions happen outside of the generative model itself. So that brings me to the difference between a large language model and a generative AI product. These are two concepts that I think the discourse tends to conflate, but they're actually completely different things. So this white oval represents base training of a model. For our purposes, the sort of language generating transformer model that I've talked to you about. Now, a base model such as this requires massive amounts of data and computing resources to train. This is the reason that you see no more than generously a dozen companies doing it, and even those only doing it maybe a few times a year. At this point, what you have is a program that can take in a grammatically intelligible sequence of input tokens and output a grammatically intelligible sequence of output tokens, but it's not the polished question and answer machine you've come to know from typing things into ChatGPT or doing code completion with Claude. That part comes from this step. Fine-tuning, which happens during model production, is somewhat more substantial than what you're probably picturing, which is maybe like shoving your entire company's documentation through Llama and then querying on that. This moves the model from the sequence to sequence phase to the question and answer phase, and it happens before the large language model's base version is released. Often a big part of this is having human evaluators select the best option from 3 answers to a given question and provide this as a feedback loop to the model. Some chat UIs are already doing this. They'll allow you to select from between 2 different answers to your question. Have folks seen this? I see some nodding, yeah. So and this step is less computationally intensive than the base training, and so that can be done, this can be done maybe once a week, this fine-tuning step, as opposed to the base training step, which can only be done a time to a couple of times a year. So once that step is done, the model can accept a sequence of inputs and give a sequence of outputs that reasonably resembles an answer. In the early days of language generation products, we could ship more or less that. The problem was that it turns out consumers have a disconcerting habit of confusing the output sequence with an actual and reasonable answer. Consumers with software engineering background, for example, could not collectively agree on the conclusion that when they asked a large language model to find the bug in their code and the output said, "I ran the code for you and I think the problem is X," that hadn't happened because the LLM had spontaneously generated a compiler at runtime and actually run the input code. That's not why it said that. It said that because it had been trained on internet text, where questions like this one that the programmer had asked often had responses that started with the sequence, "I ran your code for you and." If professional software engineers confuse language generation with language understanding and become upset at the suggestion that a sequence of output tokens are a lot less likely to factually describe the spontaneous invention of automated compiler generation than they are to just be false, how can we expect better intuition than that of the general populace? Conveniently, tooling rapidly improved. Now, generally today, when you use a product like ChatGPT, your input doesn't get fed straight into a raw large language model whose output comes straight back to you. Additional models surround and support the language model to provide you with answers that are more likely to be what you want. Consumers use these tools to accomplish all sorts of tasks, and supporting models help adapt to those circumstances. So for example, large language models, like most machine learning models, accept a number of hyperparameters. In the case of large language models, some of those hyperparameters guide how the model generates sequences of output tokens. 2 in particular that you may have heard of are temperature and top P. I'm going to elide the specifics of how these work. If you'd like to talk about it later, please come find me. I'd be happy to chat. But long story short, higher values for these hyperparameters make sense for working with a model on creative brainstorming, and lower values make more sense when you're looking for more rote, platitudinous logical output. The UI of these tools doesn't let you set these yourself. Instead, supporting models take in your query and set these hyperparameters for you. Even more recently, these products have attempted to resolve some of the hallucination problems by adding supporting models that identify the tools your query would require and including those tools in the product. So if you ask a math problem, Instead of outputting a sequence of grammatically permissible tokens, a supporting model might identify that this problem merits a calculator and attempt to plug the figures into a calculator API. You ask a coding question these days, particularly for a common and well-supported language like JavaScript. A supporting model might identify the merit of a compiler and a runtime and plug the code in that you provided. Retrieval augmented generation, or RAG, also works this way. It starts with a relevancy search with the input query against the documents that you've passed in that you think the answer lives in. And then it adds the most relevant passages into the input query to the language model itself. It's not modifying the training of the model, it's modifying the query. If you're more curious to hear about RAG, again, find me afterwards. They only gave me 30 minutes. So now you have some better context as to what's going on when you type a query into the user interface of an LLM product. You have a sense of what happens in there, and that informs your intuition about what these models might get right and wrong. You should always verify the output of a large language model. You're always responsible for the impact of the work that you turn in. But suppose that we're doing that verification. How useful are these tools for the work that we do? Let's talk about some of the research that starts to give us some answers. Now, there are a number of papers on this. I've picked two seminal ones to illustrate some points that I want you to walk away with. First, the Lost in the Middle paper. Anybody read this paper? This one discusses the likelihood that a model can successfully retrieve information from a bolus of context included with a query based on how large that context is and where the answer is in it. Basically, the more information you are passing in, the less accurate the answers become. And it's particularly less likely to find the correct answer if that answer is buried in the middle of that context versus at the beginning or the end. What does that mean for us? Well, it means that even when we're including a context document in our input query, it's in our best interest to narrow down that document to the relevant section as much as possible, not just ram in a manual the size of War and Peace and hope for the best. This paper is the one that tells us that retrieval augmented generation has its limits. It's the one that tells us that, no, it's not just you. It is true that trying to vibe code on something once it hits 300 lines does in fact work a lot less well than when it's 15 lines. So this paper right here gained some notoriety as the 26% paper. Has anybody read it or heard of this one? It claims that programmers are 26% more productive with LLMs than without. I want to dig into this claim a little. First of all, the proxy metric here is number of tasks completed, and the 26 statistic is coming from the fact that the conclusions claim to have seen a 26% increase in that number. Of substantive import, in my opinion, to this conclusion, is that the paper outright says that less experienced developers showed higher adoption rates and greater productivity gains. I think this introduces a number of confounds. First of all, more junior developers are going to receive much smaller tasks, and so the number of tasks that they complete with an LLM is going to increase by more because those tasks are smaller. It's also the case that they're likely to receive tasks that require less context, precisely the Achilles heel of these sorts of architectures. And so it's more likely to be successful on those problems than on refactor a giant legacy code base. To me, this pattern demonstrates the deepening of an existing cognitive dissonance in programming education. We teach students, train new entrants, and interview candidates chiefly on their ability to write code from scratch. But as they advance in the workforce, their actual main responsibility is usually reading, analyzing, debugging, and reorganizing code that they themselves did not write. Once upon a time, writing code from scratch was 90% of computer science education and generously 20% of the programmer's professional responsibilities. Now, that mismatch is even more stark than it was because those tasks that once required writing from scratch manually now often include asking a Gen AI product to write it instead, at which point we are once again reading, debugging, reorganizing, and analyzing code that we ourselves did not write. I think large language models have not wholesale wiped out programming jobs so much as they have called us to a more advanced, more contextually aware, more communally oriented skill set that we frankly were already being called to anyway, just 80% of the time instead of 96% of the time. On relatively simple problems, we can get away with outsourcing judgment and investigative skills. But as the problems become more complicated, we can't get away with it. All right, I'm gonna need everybody to squint because the next slide is almost completely white. I warned you. So what might we take away from all this? I think there are a few lessons worth writing down. First of all, LLMs are most helpful on programming problems that are specific. To the extent that we can provide a complete, unambiguous set of success criteria, we can improve our chances of an accurate answer. It also helps if our question is limited in scope. We've narrowed down the context as much as possible. And also focused on a programming language with a robust sharing history. These tend to be languages that are well represented in training patterns. Though we don't yet have a high statistical power study on the matter, I swear to you, I looked and looked. Anecdotal evidence is pretty strong on this. Now, LLMs can help us identify implementation options, but so far they don't provide an adequate substitute for judgment. The more of our job focuses on experience-based judgment, the less these tools have improved productivity so far. This is why subject matter expertise and contextual expertise still matter in decision-making, including judgment on whether and when to trust the output of a model, even as an initial draft. Finally, by dint of the patterns that train them, the nature of large language models supports reproducing existing logic. They repeat the patterns of language that they have seen, a sort of global average, if you will, of what the internet has to say about a topic. This can be helpful when questions have established answers and when programming communities publicly adopt shared norms. In fact, the highly structured nature of programming languages makes them kind of an ideal case for language generation experiments. But what these models can't do in and of themselves is innovate, is break from the pattern of what has been said and taught in the past. The more newness you're looking for, the less you can rely on a large language model's output in and of itself. The question I'll throw in here that I think I still don't know how to answer is how today's junior programmers, aided by LLMs, will navigate the challenges that we currently use judgment and experience to manage at the senior level. With some understanding of the sorts of problems we can expect, I think we're here. What skills does the AI-enabled engineer need to excel at? This is where we venture out of the territory of empirically supported claims and into the territory of my personal perspective. But it is a perspective informed by the realities we've already discussed and corroborated by my personal experience and watching my students try to do this. The first skill set's investigative skills. We need to be able to scope down the area in which we are facing a problem and learn to ask specific questions about how our assumptions differ from the ground truth. I find this to be a woefully undertaught and undervalued skill among engineers, precisely because we tend to view debugging or familiarizing ourselves with the system we're working on not as part of our work, but as a blocking obstacle that distracts from our actual work of plowing through features and system changes. I think this is a deeply flawed way to view our profession, and it's one made even less accurate than it already was by the advent of tools that can plow through feature development for us, provided we possess the investigative skill set to identify and understand when and how those solutions make inaccurate assumptions or need to be fixed. The second skill set is evaluative skills. We need to select from a range of implementation options based on how those options' benefits and shortcomings fit the bill of our specific situation. I think we often ally this skill set as engineers as well, this time by deferring to what we've read or heard as a best practice. This works fine a lot of the time, but many of your worst nightmares made manifest in code are the result of engineers applying a practice that, while considered best, did not fit their circumstances. I think engineers, particularly at more senior levels, need to take stock of why best practices are what they are and determine whether those reasons make sense in each situation where they're being used. More granularly, I think it falls to engineers to learn to specify exactly what their design decision criteria are, decide explicitly which of those are optimizing criteria and satisficing criteria, and then determine how each of their options stack up against those criteria. An LLM can tell you what most people say to do. It cannot tell you what you should do. The final skill set is innovation skills. We need to learn to proactively search for the shortcomings of the available options and consider solutions that haven't been tried before. These are precisely the solutions that a Gen AI product cannot produce by handing us a global average of what the internet has to say about a topic. The task falls to us, I'm afraid, to understand how our status quo falls short and figure out what we could change to improve those shortfalls. We need the ability to proactively identify who our systems do not serve, or who they serve poorly, and why, and how to fix it. I'm confident that these skill sets give us a greater purchase on our roles in a Gen AI-enabled world because I have seen them give us greater purchase on our roles regardless of the availability of Gen AI. And I see the reasons for that exacerbated by the use of these tools in development contexts. Should we manage to focus on these three skills, I think we can leverage these tools in their most consistently successful function as an aid to our process, to aid us in being productive, not in the sense of generating more slop for GitHub, but instead in the pursuit of a more rigorous, compassionate, thoughtful approach to software development. Thanks for listening. This is where I am online.